And Mogens Blanke, he's a professor here at DTU Electronics, and will now make a speak about some of the research taking place here, because that's the idea of this whole event here, to get to know what is Siemens dealing with, and do we have any research here at DTU that could be in some way connected to this. So look forward to hear your presentation. Thank you, Mogens. 20 minutes for that.
Thanks very much. And while we're waiting, we're not waiting any longer. Professor Wegner, Dieter mentioned that we have started a collaboration and a small corner in the future dreams. Might have some ideas from DTU, and this is why I will not talk about that, because when we get bright ideas, we should first disclose them in a smaller audience, namely the patent lawyers. Instead, I will supplement what Dieter already said by giving you examples on what will be and done, we anticipate, in the future power grid. This is a very important system for society. We have the benefit of having a very stable power supply in Denmark, but that might not be like that in all future. The research in this area makes sure, we hope, that the future sustainable power systems can operate in a secure way. With the increased penetration of wind turbines with solar energy that being fluctuating sources, we see that we will shift the production of energy from one part of the country to another part of the country as sun shines and wind blows. This gives us some challenges, and I'll show you a couple of these. This research is supported by the Strategic Research Council. We have EnergyNet DK, we have Siemens from Erlangen, some partner universities, and from DTU Electrical Engineering, it is the CEE Center, Jakob is sitting here, and the automation group who are collaborating on that. But let us look at why should we be concerned. We are in the green area now. We have a secure supply, and we more or less never encounter a disruption of power. But when we do, it's viewed as a catastrophe. There was a power outrage in New York for about 48 hours some years ago. And what should people do? Well, 9 months later, we saw the result. The burst rate increased dramatically. And that's, of course, nice. But it's not so nice to be without power for all our computers, for our manufacturing, for our household, for our heating. So sometimes when we have a situation where we have fluctuating production of energy in the future system, we will come from a secure operation into a yellow operation where we still have stability, but if just one thing more goes wrong, we will end up in an unstable situation. And what is unstable situation? I was looking for a slide here. Unstable situation. In 1996, the time scale here from 0 to 80 seconds, so we're talking about 1 minute. This is a picture showing the megawatt of power flow in California. And what we see here is that 7.5 million people had no power. This is a particular type of instability where these generators get out of synchronism. It's very difficult for an operator to react to this. Sometimes this is a very gradual development so that the operators might not notice this instability before it has reached a magnitude where it's very difficult for him to do something about it. Other times it goes too fast, as here. And when does this happen? It happens when we have heavily loaded power systems, where we don't have a balance between production and consumption. And then we have to do load shedding. That means switch off a number of consumers, a very large number of consumers. But could we do something about this? Yeah. If we have an ability to do automated fault diagnosis, fault detection and isolation by observing what is going on in our system, and this is a generic technology, it is not only very useful for power systems, it's also useful in manufacturing and production. Having had an assessment here automated in real time, within milliseconds, we know what is going on. Could we then help the operator by reconfiguring something such that automatic control could take care of this instability situation, such that we avoid that it develops from just a start of instability to a load shedding situation? I will show you a specific case which relates to the California incident. Namely, we have these huge generators that produce power for us. They are distributed. That means they are at different locations. There is a small control box here, which is a power system stabilizer, and what it does is to make small control actions to the generator in a timely manner, such that we avoid instability. When one generator goes down, however, we may have a problem. This could be the generator that trips, that means it shuts down because of overload, and then the remaining generators very easily get out of synchronism, and we have the blackout. So what do we want to do? Let us look at an example. I have 4 generators here. There's a distance of 200 kilometers. And what happens if this generator fails? In this situation, and this was a famous textbook example, one of the authoritative textbooks in the field illustrate what is this instability caused by. And you see the instability develops over close to 10 minutes. The operator can't see anything here. When he discovered it here, it's too late. And the reason was that we had one of the generators that could no longer be controlled. So what do we do? Now the control system ideas available, one of these are to apply what is called a virtual actuator. So could we in some way use the information that we have over the network to control the remaining active generators so that we avoid this instability? The answer is that if we have centralized overview of what is going on, and if we have the ability to communicate over the network in real time with the other generator control systems, then we can save the situation. And the way to do that is not entirely easy, but it was shown in a recent paper by these gentlemen. Jan Richter is, by the way, from Siemens. The whole problem is nonlinear, so it's not easy to tackle. When we have the small fault developing, then we see after 10 seconds we decide to reconfigure. And what you see is a small fluctuation in the excitation signals to the remaining 3 generators. But what we avoid is the instability that develops. So this is one use of the network. Another example, I should say one thing here. It is actually rather simple. to implement this in real life, because what we do is to calculate a command signal and just add it on the individual generators. So it's not a big thing to, with respect to implementing alternative software in controllers. If we have a real unlucky day on the same system, where we have a trip of this line, and then of this line, and then an increase on this point by first 10%, then 10 other percent, and so on, then we will have a bad day again, because after a while, all generators simply shut down. So now we have the 4 generators, but because of the overload situation, we get into trouble anyway. And the time-wise duration is about 10 minutes here. What could we do about it? Now, because we had a change in the impedance, we lost 2 of the transmission lines, we have to change the parameters of the power system stabilizers that are at the remotely located generators. So we need information over the net to this wide area control, and we need to do a little bit of controller redesign to accommodate what has happened in our controllers. Now the purpose here is to obtain stability, and this can be done. And by stability, those of you who are electrical engineers will recognize this. These are the eigenvalues of the system. All the dots is a dynamic part of the system, and many dots mean that we have a quite complex system. We would like to remain to the left of these 2 lines, of the red lines. Then we have sufficient stability to achieve what we want. If we just do a brute force approach to this, then generator 1 has 8 states. That means internal modes of its dynamics. Generator 2 the same, and so on. The amount of communication that we need, the amount of signals that we need, are shown here. Input to generator 1, 2, 3, and 4. So all generator control systems need to talk with the other ones. So everything here which is outside the red boxes will be network communication. And for a real large system, this will be too much. So the idea was, can this be optimized? Can we reduce the net traffic? And the answer is yes. It has some impact on where the eigenvalues of the total closed loop system are placed, but we are still according to the specifications. And this can be optimized and optimized. And finally, wow, we just have one signal between generator 1 and generator 2, and that's it. And we obtain stability on the network. And this is feasible, because sending just one signal is not any big load on the network. Now we have 4 generators here, so it might be more when we have a large number of generators in the network, but still the ideas here show that we can do some optimization, and this will then be response to these various events on the unlucky day, first tripping of lines and then increase of load, but we remain stable. Now, what are the challenges then? It always looks easy when somebody from a university steps up and says, yes, this is the theoretical way to do this. No worries. But there are challenges. We need to change the idea that power systems are built by giving an ability from a wide area network to the individual parts of the control system. That must be done in real time. Actually, this is, I think, much better than having the operator sitting in a centralized control center and sending manual commands, because it's faster and we know what is going on. It's, I would say, more reliable than the operators because it has been designed. Are there any power systems operators among us? Ah, phew. But what are the challenges of this network control? Communication bandwidth, of course. We must realize that we will have packet loss, we will have a random delay, we will have measurements that are quantized, that means they are just stepwise. We will have challenges with the scalability because power systems are huge. We will need further research in distributed fault diagnosis, and in particular make the fault diagnosis part very reliable. And we should have distributed fault tolerance control. So there's a lot of very good research to be done in the coming years. So with these two supplementary views on the future, one with the overview by Dieter, and this much more detailed as meant as an example of what could you do if you had these nice network control possibilities, I will end this presentation.
Thank you, thank you. Thank you very much. Could be interesting if Siemens and D2 together could stop electrical disruption like we saw in New York, maybe in the future, we don't know. So, now it's for you to work. You heard these really interesting presentations, and now I would like you to think about, reflect on this, and maybe look in your own back catalog. Are you having research going on or knowledge about activities or other research programs that in some way could help this connection to develop in the future? So the way I would like to do that before we take questions and comments for the two speakers is that if you turn to your neighbor, maybe 2 and 2, and try to reflect on this for a while. I want to make sure that everyone has someone to talk to, so maybe some of you will have to move a little bit, or you could be free together if that's the only way we can make it come together. So please reflect on this. Can you see any opportunities for cooperation in the future with what you know about what's going on? Thank you. Yes, very much. We are having some very engaged conversations, which is a good sign. Now, I would like to pick a few comments, questions, ideas for our two speakers here, and then they will comment on that. I will also invite you, if you have time during this session, to write down any idea you have, any reflection, so we can save it afterwards. Then we will get much more value out of this whole thing. But anyone who has something they'd like to share with us or for the speakers? Yes, maybe you can say your name and where you're from.
I just want to make it known that on behalf of the Rector, we are investigating the formation of a consortium in value-added manufacturing and intelligent production systems, together with TU Munich and possibly a few other universities. And I think a lot of both of your presentations would fit in very, very neatly. So I would really like to talk with you in the breaks about this. And the window frame for this is early 2016, but we are now trying to get a consortium together.
So I'm looking forward to meeting you in the break. Thank you for your comment.
Okay, some immediate comments on this, or in the break? Okay, thank you. Yeah, and one question, I'm sorry before you say, can you actually hear at the back if we don't use a mic? Is that okay to do it like that? Or do you prefer a mic? Yeah, we can use a mic. Okay.
It's easier.
Yeah, thanks a lot. My name is Michael Weinhold, CTO of Siemens Energy, and we were just very intensively discussing amongst what you presented, and we're in the process of having an application at the German funding, national funding, and we're just discussing whether we could also incorporate Danish aspects, because what's happening in the grids, we are having less and less rotating mass and more power electronic based generators.
Yeah.
So the system dynamics are changing. We are also having more and more distributed generation, and I think there are a lot of connecting points to explore this. So we will figure that out. We will set up a telco to discuss how we can get closer together here.
Oh, that's good.
Thank you.
Thank you. Mogens, you like to say something?
It's very interesting you mention this rotating mass, because the examples that we showed here, that we simulated, are with huge generators that can produce like 1 megawatt each. And with the wind turbines and pure electronic control of that, you have literally no inertia. So what about this instability that today takes 10 minutes? Will it take 10 seconds, or will it take 1 second to develop? We have seen oscillations in one of the wind parks of Dong Energy in England of around the kilohertz scale, and that is an oscillation on the power system. So, I mean, it's a lot of megawatts that are behaving as they should not do, because they're just fluctuating from one end of the park to another and not getting into the
grid.
The grid of the consumers. Okay, thank you. One more comment, thought from you? Okay. I'm really delighted to hear that already we see a lot of different connections popping up, so I think that sounds really interesting. I like what you were saying. You used the metaphor of a Tour de France team. So, and still we are having Industry 4.0 ahead of us in 2030 or something like that. It will probably something like that. So, if you should set a team with DTU and Siemens, what would it look like? How could you complement each other? How could you help each other? Have you some thoughts on that?
No, we are already working together. I mentioned that on the self-healing. I mean, Industry 4.0 takes a lot of advantages of already existing technologies, developing some to the next level, but that is already, let me say, we are working together. But there are other things, for example, to bring the real-time network information from the shop floor to the office floor. So you have to solve a challenge, because you have to give the data streams a semantic describing the branch-specific information. So to say, for example, I'm a cyber-physical system from an oil and gas field. I'm a cyber-physical system from a machinery, machine builder, machine tool, and so on. So you have to describe that on the engineering level. Then you have to find data structures to transform it. So that is not the question, which protocol do you need on the OSI 7 layer model on the level 1, 2, or 3, 4, where it's already given by the IEEE 801.11 standard, or by the wireless LAN standard, or in the level 3 or 4 is TCP IP. But there on the level 5, 4, 5, 6, and 7, there are some things which are not described yet. And for example, there's one model that is OPCUR. It's the foundation where we defined the data structure, and that is not yet well known, but that is capable for handle data. But that is only one side of the matter. The second is that you have to define the model describing the detail world in the field. So you have to find models, engineering models to describe, and then you can put it on a level 8, perhaps on the data. That is yet not defined. That is to do. And first we have to find an idea how to do. So there is a lot of things to do. So when you see in the newspapers some companies saying, okay, the Industry 4.0, you can buy it from us, then it's, I think that's marketing. That is that is from a technical viewpoint bullshit, but from a marketing viewpoint you can do it perhaps, but it's not smart from my viewpoint. So there is a lot of things to do, and I think we want to make in DTU an approach on that. We have a workshop on mid of December where we try to find a way, how we can make an, let me say, Industry 4.0 approach where we want to combine DTU compute because of IT and mathematics, DTU electro for the automation and electrical equipment, and DTU management engineering for the sustainability and engineering aspects. So we try to form up a team on that. We will see whether we can do something. I personally believe that we can do a lot of things, and that we are teaming up in that manner. That would be perfect. But we will see on the workshop.
Okay, that's good. I saw you were nodding a lot during Mogen's presentation, like, wow, this is interesting. We've got something.
Yeah,
Okay.
But perhaps as a supplement to what you said, Dieter, how fast things happen is sometimes a big surprise. We were driving along in an orkyard out in Tostrup a few years ago with an autonomous tractor. And it was a big surprise to me to learn that, well, I have it from this morning's newspaper, but a driver's license was issued not to a person, but to an automation system in California yesterday.
To the Google car, whatever.
Yes. Driving license for the Google car. Wow. I wouldn't have dreamt that that would have been possible within such a short time. So I'm sure we will see a development. Sometimes things kind of perturb, but with a massive effort as Google has made and as Siemens will make now, it might not be 2030, it might be even before.
Yeah, you mean 20 earlier?
Earlier, yes.
I mean, in the consumer electronics or in the consumer market, I totally agree with you. You will have it, you will see it faster and faster, and in some types you are already facing. For example, the smartphones and all the capabilities on smartphones. But be aware, if you are in the shop floor, you have to consider some rules and especially some legal requirements, and that is a difference, I would say, to be in the, like we say, private life with consumer goods, or to be in the heavy duty equipment stuff of production plants. So there is a different world. So I believe, yes, it's fast going, and Google and Apple and so IT-driven companies will change faster the markets than we want to have, but at least there are some hurdles, and these hurdles are not coming from the technical viewpoints, but from a legal viewpoint. And to change legal framework, I would say that is not so easy. So that is defending that word a little bit.
Okay, so we have to stop here now. Thank you for a lot of thoughts, and I'm sure your cooperation might speed up things in the future as well. So let's see what happens. So thank you. Let's give our two speakers a hand. Thank you very much. And now it's time for our next session. As you see, we try to make double presentations, two things that are linked together somehow. And we are very happy if you try to help us to see different connections. These will be the next two presentations before lunch. So we will have two 20-minute presentations, another talk, and then lunch.